All right then. So we have a couple of things happening here. One, always, the original function has this derivative function connected to it. The question then becomes, if I change the function, how is the derivative function related to it? Can I see a pattern beyond using the limit definition? Okay, well, to do that, let's stick to our basic functions. And after I've now investigated and figured out x squared, what is my next basic function? Probably x cubed. That's the next polynomial that I have in my library. So let's have a look at it. Let's make a new page here. And of course, with a more complicated function, I'm going to get a more complicated derivative. That is reasonable. Now again, my goal here, of course I can see the graph, right? I know the graph. It's one of my basic functions. You should all know the graph immediately. Whether I can graph it neatly is another issue, but it's a little wobbly there. There we go. There it is. Different graph. So I'm still asking for slope values. What are these slope values? As I pick different x values to be interested in, sure, I can go and pick a specific x value, plug in the limit definition, and say, for example, let's say I want to know the slope at x equal to 1. Well, that is the derivative at 1. I set up my limit definition, f of 1 plus h minus f of 1 over h equals. But I know that even if I did this, which might not be a small amount of work, what if you want another x value? What do I do then? Do I have to do this again? No. Let's just stop this before it even starts. By just keeping the x value open. Let's maybe call it a c, if it helps you. Not be specific. It could be any x value. Let's see what happens then. Now, yes, this is a more complicated function, so the calculation will be a little bit longer, perhaps. But let's have a look. We have to see a couple at least. So it's x cubed, so it's c plus h cubed minus c cubed over h. All right. Now I have a bracket cubed. Now we can, maybe on the side here, c plus h cubed. Maybe you remember how to do this. Maybe you want to look it up. Maybe you want to multiply all the brackets and FOIL them out. When you FOIL them out and simplify them, you should get, actually I'm not going to do it in the line. There's no need to write it twice. You should get c cubed plus how much? Three c squared h plus 3ch squared plus h cubed, and then I have this minus c cubed still there, just squeezing in over h. And now you see that the two c cubes cancel. And in what's left, I can factor out an h, 3c squared plus 3ch plus h squared left in the bracket. Yeah, more complicated function, more algebra. It's going to happen. Then I can cancel out the h's. And what I have left is, remember, h is my variable. The c is a number. I just don't want to specify it right now. So this is a polynomial in h, which means I can plug in 0 for h, and I get 3c squared. This is now my formula. If you want to see it as a formula, you can, but it's actually a function. This now tells me original function. If the original function is my basic cube function, then the derivative, which is a function because it depends on which x value I want, whether I call it c, whether I call it x, doesn't change the fact how it's calculated. There's another pair, original and derivative. But I have to do the limit definition. Fair enough. That's a lot of work. Another one. Next one up is if my function is the x to the 4 function. You're going to have to set this up. It's going to be longer and longer because of this bracket to the 4 every time. Like more higher power here, and more work is involved. I'm going to save you the trouble. If you go through the same motion, limit definition, you're going to get the derivative as 4x cubed if you've done everything correctly. So now let's have a look here. Let's have a look. We have original function. We have a couple of examples now, so we can make a list here. And we have the derivative. Original function, f of x, x squared. Derivative is 2x. Original function, x cubed. Derivative, 3x squared. Original function, take my word for it, do it if you want to, absolutely. Go through the motions. The limit definition just gets longer and longer and more tedious. But I have to do it to convince myself. I have done it. So feel free to do it as well. I get 4x cubed. Let's do one more. Now it gets very tedious. But if you have the time, convince yourself by way of the limit definition. I'm not making these up. Limit definition gives me the answer. X to the 5 times x to the 4. Is there a pattern that I can see that if I have x to the power of n, how the derivative is linked to this function type? Of course, it's very specific. It's a single power of x. Is there a link? Can you still hear me? Am I talking to myself? There's a very high chance I'm talking to myself, which is a shame because these next few lectures are extremely, extremely important. Now, whether you see the pattern or not, I think everyone would recognize there is a pattern here. Definitely. It's not really hidden. The coefficient keeps increasing, so it's reasonable that the coefficient should be an n. It's the same as the power of x, right? And the new power of x is 1 less. And there we have it. There we have it. Now, we're not saying as much as you think we're saying, but we're saying something, and it's a good step in the right direction. If I have a very basic function, a single x to the power of some positive integer, then I've now gone up a few levels here. Then I can find the derivative without touching that limit definition, and that's ultimately my goal. My goal is to be more efficient, and that limit definition is the opposite of efficiency. It is time-consuming and tedious, and something I honestly never want to do. I have to do it once, or a few times. But after a while, I'm done with that thing. Don't avoid it completely, but do it enough to realize that you don't want to do it anymore. which means I need to find these links between the function and its derivative. And now I've seen that if I have a function that looks like x to the power of some integer, I have a formula, if you will, that links the function to how its derivative looks. We'll call that the power rule. Now, I don't like the word rule because it feels made up. I'm making up the rules. You have to live by them. That's not the case. It's more a property. It should be called the power property, but it's not. It's called the power rule, and everyone uses the word rule. Power rule. But understand, it's not made up. It comes out of the limit definition where we do it over and over and over, and we see a pattern, and that is how it behaves. Now, of course, we're slowly building up our functions, right? Right now, we can't do all the functions, even the basic functions that we have, we can't do them all at once. So we're looking at our polynomials, and we've done enough to see the power rule is what the link is behind these kinds of functions. Of course, we have other basic functions. Oops, let's zoom in one more. We have other basic functions, and there are two of them. It doesn't matter which one you do next. Because of the questions in the chat, we'll do 1 over x. That was another function, and that wasn't a bad function. It was a nice function, with the exception of its vertical asymptote. It was well defined everywhere else. It has tangent lines that you may want to know about. So the question of slopes of tangent lines, the derivative question, it's a very appropriate question. It's a basic graph. We should be able to answer that question. Okay. Now I'm looking at the basic one. I'm not looking at transformations on this. That could even simple transformations could make the derivative question too hard for me right now. So if I want to know at x equal to c, what is happening? Well, that's the derivative at c. There is no way. It's a new function as far as I'm concerned right now. I have to go through the limit definition. As much as I don't want to, there's really no choice. There's really no choice here. And I have a general as well because I only want to do this once. No, I don't want to do this again for this kind of function. New function, yes, I have to do the limit definition, but at least I want to do it only once. So now I want to see how this function simplifies. So I have 1 over x. So this is 1 over c plus h minus 1 over c, all over h. I'm still dividing by 0, so I can't plug in the limit value here that I'm interested in. So I have to keep simplifying until I make some progress, which means I have to put the top two fractions together over a common denominator, which is just their product. Then it will be c minus c plus h. And of course, these are all prerequisites. You should be super comfortable with simplifying algebraic expressions. Then this is h over 1. When I divide by a fraction, I multiply by the reciprocal. I'll leave this to be one simplification at a time. So it's h times c plus h. See, it's such a simple function. It's one of my basic functions. And this limit definition procedure is just annoying. Imagine for even slightly more difficult functions. This is not something I want to do very often. C minus c, and then I have a negative h. And I still have an h at the bottom and a c plus h. So the h's cancel, which gets rid of my problem, dividing by 0. But let's just see it anyway. Now, it's nice to sit back and watch me do it and see, oh yeah, let him do it. I'm not going to do this limit definition. Everything I do, that's something that you have to be able to do. Okay? You have to be able to do this limit definition, at least in one question. When h is 0, this is a rational function in h. H is my variable. I can plug in 0. I get negative 1 over c squared. because c plus 0 is another c. So it's not that bad. You do it a few times, it's okay. So if my function is 1 over x, then my derivative is negative 1 over x squared. Is there a pattern here? Does the power rule apply? It does. This function is x to the negative 1. If I rewrite this derivative, derivative. If I rewrite this derivative, I get negative x to the negative 2. So if I take this version of the function, I move the negative 1 to the front. The new power of x is 1 less. I do get that. So the power rule still works. So really, even though the basic functions were fundamentally different from polynomials to rational functions, potentially, the power rule handles them all in their basic simple form. So now I can go back and update this. Power rule works for n being any integer, positive or negative. Of course, not 0, right? That would make no sense. I wouldn't have a function then of the same type. So it could be positive integers, it could be negative integers. It always works. If, for example, I have the function as, and we'll stop in a second, x to the, let's do it like this, 1 over x to the 5. Well, I can rewrite that as x to the negative 5. And then the power rule simply says, put the negative 5 in front, the new power of x is 1 less. I can simplify that if I want to, I might want to, or I might not want to. The power rule allows me to use the link that I've established outside of having to do the limit definition. I can sidestep all that tedious work that the limit definition gives me. I can sidestep it and find the derivative immediately. Now, of course, I have to explore this further. These are still very basic functions in their appearance, in their structure. I have to take my time. And unfortunately, right now, I've run out of time. So we have to see if the power rule can be extended to more functions. And once we've extended that as far as we could, we have to see, okay, well, what else is there? When does the power rule not work? What do I do in those cases? And so on, so on. But we'll find that the power rule and some other basic properties can get us much further than you think. But it takes time to explore that. It takes time to find all these properties. But once I have it, applying them will become much more straightforward. But it's better to do this exploration, taking a little longer, letting things sink in, and understanding where these come from, what they're saying, what they're not saying. And then when I apply them, they're not as strange. Rather than me just giving you a list and you having to use them, there's no understanding, there's no connection. If I explore these and see where they come up and when and what I need and what I don't need and all those things, I'm more connected to it. But it takes time, and we have to continue this discussion next week because today is Friday. So there are many cases where the power rule won't work, right? If it doesn't look like x to the power of something, exactly like this, positive or negative integer, right now, the power rule is not going to help me. What do I do? But it'll take time to answer those questions. The good news is that there is a lot we can do. We just have to go and figure it out once and then practice using it. But that will have to wait for another time, and that time will be Monday. All right. So not much to do. If you have catch up to do that. Don't bother with our problem book chapter 5, topic 5. Don't worry about that right now. Practice the limit definition, because there's always a question where you have to use the limit definition. So that has to be something that you can do at least once. So if you have to catch up, if you have to review anything, review simplifying algebraic expressions, things like that, there's always stuff to do. But we're not quite ready to handle the topic 5 problems until we do this discussion, continue this a little further next week. Until then. If I have my function, which let's just say in power of x, then we've established before that the derivative is going to be the power of x multiplied in front, that's a coefficient now, by x to the power 1 less. And we call that the power rule. Now this works, this is true for n. We started with x squared, x cubed, and so on. So it definitely worked for positive integers. Oh, this writing delay is horrible. I know it's D2L that's doing it. I'm just gonna, just give me a second. I want to see if anyone is in D2L, because otherwise I'm closing this. It's nonsense. It's making my writing sloppy. It's making everything laggy. It's not efficient. Just trying to see who's in here. Yeah, I'm the only one. I'm going to stop it. Give me a second. Get that nonsense out of here. Okay, that should be better now. But now if my writing doesn't improve, oh, now I don't have an excuse anymore. Ooh, I didn't think this through. Anyway, then we also looked at, so for example, x squared, x cubed, and so on. It all worked. We did a few of them with the limit definition. It was tedious. And then we noticed a pattern, and we just extended that pattern. Now, that doesn't qualify as a proof. You have to do it in general, but that using an x to the n is a little bit messy. I don't want to show that. It's a little outside of our focus, proving these things more formally. Then we looked at 1 over x, x to the negative 1, and we saw that it also works for n being a negative. Oh yeah, now the writing is way nicer on my end at least. Oh, so nice and smooth now. Also n negative integers. So that's quite a range. And if we did, for example, a couple here, if we say let f be x to the 5, then the derivative is going to be 5x to the 4. So I just noticed that formula. If I look at a random negative power of x, let's say negative 7, then the derivative is going to be negative 7 goes in front, x to the 1 less, which becomes negative 8. So I always subtract 1 from the original power of x. Okay. So that's quite a bit. It's good progress with one rule. I don't want to call it a rule. One property that is coming from the limit definition, we can sidestep the limit definition completely, and that's my goal here. Let's now look at another example. Let's say I have a function here, and another basic function that I have is the square root function. I want to know what the derivative of this is. Well, it's technically not what I've seen before, so I have to go with the limit definition. That first time, whenever I see a function for the first time, or a type of function, I kind of have to. I don't know if we have space. I'm just going to go with it. So whether I call it C or X or whatever, some people get a little confused if I use an X here, still at this early stage. So I'll use another letter, but doesn't change the limit definition at all. It's whatever X value, whatever X value I am interested in. I just don't want to pick a specific number, because then I don't see what the derivative relationship is with the function. I want to see this function aspect so that I can maybe see something that allows me to get around the limit definition and all its work. It is always there. That doesn't mean I always want to do it. So now let's see what we get here. Of course, we can't just plug in 0 for h. I'm going to have to see what the function is. Now it's the square root function. So inside the first one, I get a c plus h. Inside the next one, I get a c. Now, these kinds of things, yeah, they can be difficult. And this is a basic function. This is my simplest square root function. And even this, people might feel, I don't like this at all. Fair enough. But I want to show you, I want to at least see once how the limit definition has to be used to establish more efficient rules, at least in the beginning. So now what on earth do I do here? The form of this limit, if you look at it, and we should always look at the form of the limit, of course, is 0 over 0. Because at the top, I'll get a root c minus root c, which is 0, over h being 0. Yeah, 0 over 0, unfortunately. So that means look at the function, look at what I have, and see if I can simplify that. But looking at it, it's not a rational function. I don't factor it. I don't do things in the same way. It's a different kind of function. There's a little trick that I can do that is something that you don't have to come up with. You just have to see it once and sort of learn from it. I'm going to multiply this whole thing by 1. And because it's by 1, I haven't changed a thing. But now I'm going to see 1 as 1 over 1. Still haven't done anything because I'm just multiplying by 1. Now I'm going to write this fraction this 1 in a very, very fancy way. I'm going to write it as the root of c plus h plus root c over itself. C plus h plus root c. Why? Well, we'll see in a second that it's going to work. And because I have the numerator and the denominator the same, I've only multiplied by 1, and I haven't changed anything, so I can still say equal here. Now I'm just carrying the limit with me here until I can simplify this in some clever way. So now I have at the top the root of c plus h minus root of c times root of c plus h plus root of c. Over the bottom I have an h, and then I have the root of c plus h plus root of c. Okay, but the top is more important right now. The top is what's important, because I remember that if I have an a minus b times an a plus b, that simplifies to a squared minus b squared. It's the difference of two squares. And that's exactly what I have here. The same thing's in the bracket, except one's a minus and one's a plus. So that means I have the first one squared and the second one squared. And my bottom stays the same. Nothing is happening there for now. So now I'm just going to make a new page while you think about what happens at the top there. The square and the square root are sort of defined to cancel each other out. It's kind of what the square root does. So I'm just going to continue up here. I'm looking for my derivative, right? So I have, limit. Let's just write the limit there. We're not ready to really use that part. It just goes with us everywhere. So this first one is going to be c plus h, because square root and square they cancel each other, c plus h. The next one is just a c. And then I still have the messy bottom portion, unfortunately. I'm not too worried about that right now. I'm just carrying it with me to hopefully see something eventually. So now I have this c and this c canceling each other. So what do I have now? I have only an h at the top. And then I still have the same bottom, c plus h. Oh, a stupid truck in the background here. Hopefully it doesn't bother anyone too much. Now the h's can cancel, and I'm making good progress. And I have 1 over c plus h square root, c square root. Now what is the form of this limit? It doesn't really matter. What matters is it's not dividing by 0 anymore. There's no zeros anywhere in numerator, denominator, nothing. So this is well defined, so to speak. It's defined at h equal to 0. The limit is just going to be what I get when I plug in 0 for h. And then I get 1 over 2 root c, because I have 2 of the square root of c. Now I know that was a little long, messy, something I should see though. Agree to disagree, but you should see it once. This trick, whenever I have the root issue in a limit, often this trick is by multiplying by a fancy 1, so to speak, can help me simplify things to a point where I can eventually just evaluate the limit easily. But regardless, so if whether you perfectly followed that, whether you need to look at it again, doesn't matter. The point here is, if my function is the square root function, then the derivative function, whether I use a c, whether I use an x, doesn't matter. It's an x value, just temporary placeholder, is 1 over 2 root x. But notice that the square root of x is x to the 1/2. So I can see the function, this basic square root function, I can see as power of x. And so far, all the powers of x that I've looked at seemed to fit the power rule. But I haven't looked at fractions until now. The roots are fraction powers of x. Can I simplify this guy to write it as a power of x? Well, it's definitely 1/2 derivative here, right? Because the 2 is in the denominator. And then I have an x to the 1/2 at the bottom, which becomes x to the negative 1/2 when I move it to the top. Now, what would the power rule suggest? The power rule says take the power of x, take the power of x, move it to the front. Okay, the power of x was 1/2. It is at the front now. And then the new power of x is 1 less. Well, 1/2, what it was originally, minus 1 is negative 1/2. So the power rule works in the sense that following the power rule gets me to the derivative function as well. And in fact, that's true for all the fractions. In fact, I'm just going to put it over here. power rule is true for all real numbers, real values of n. Yes, integers, negative, positive, fractions, anything at all. The power rule works. So it is quite powerful. Get it? Power rule, power of x, powerful? No? Okay. In that it covers a lot more functions than we originally might have thought. Okay. Power rule. Any power of x, if it's x to the power of something, the power rule will help me. So it's actually a very, very important and I don't say versatile property. Versatile, sure, let's go with versatile. It's a very versatile property in that it handles a lot of functions, but still basic, right? It still has to be only x to the power of something. I don't have a lot of flexibility, but in terms of what that power, that exponent can be, lots of flexibility.
Please remember to click the like button if you enjoyed the video, and to subscribe if you want to be notified of more videos. Thank you.